Oof.
Oh, I forgot to record. Okay, so I guess people in this
I think I did hear it start at the beginning.
podcast. Anyway, yeah. So they're very easy to overfit. Because the thing about decision trees natively, like without any controls, is that they're going to keep splitting and splitting and splitting until the purity of every like leaf node in the tree, like at the bottom, is one, is zero. It will only be one class at every leaf node at the bottom, which is great for the training data. Wow, you can get your training data to be 100%, but you can't guarantee that your testing data is the same pattern. So that's an issue. So what do? You try and put like controls on it. Like maybe you say the tree can only be this tall, or it has to have this much data to split on. But there's so many ways to do this. There's so many different controls. For example, on splitting, for finding the impurity, these are the most three popular methods. Three is entropy, gaining impurity, and log loss. It's not important to even know what those. All you need to care about is that you're going to use gaining. But there's all that, and that will change how the tree splits. And then you can have ways to control the model. Like you can say how maximum the tree has to be, the number of samples you need in order to split the data. Like how many nodes can you split? How many nodes do a leaf need? Or if you're trying to have different inputs, how you treat splitting your categories up. It's just a matter. And second, this is what is known as a greedy algorithm. And so for those not familiar with the term greedy, you haven't gone to that part of classes. Basically, greedy means at the current point you are at, that is the best decision to do. Like for example, if I wanted to eat healthy and I was given a hamburger and vegetables, the correct decision would be to eat vegetables. But then let's say after I ate vegetables, I didn't have any opportunity to eat any more meat. Now suddenly I'm stuck just eating vegetables for the rest of my life. And no protein or anything. It's just vegetables, no beans. That's not healthy. You need your protein, you need your carbs. But let's say if I ate the hamburger, then there were other possible decisions of, oh, you can now eat a salad or you can eat carbs. There's a balance. But when you were at the very point at the start, the best decision was to eat vegetables. So that's what greedy is. At the current decision you are making, you make the best one, but that's not a guarantee that that's the optimal decision. So that's an issue. So decision trees, sensitive, greedy, we need some sort of way to cover for these deficiencies. And so this is where we get to something called ensembling. And ensembling is basically you just combine a bunch of models together. Basically, by combining them, you kind of increase the accuracy. This is popular for that. And you decrease the effects of an overfit model. Like if you have one model that got super overfit, if it's part of an ensemble, that overfitting has a decreased effect. And for decision trees, which ensembling is very popular with, combining multiple trees together is known as a forest. Shocker. Crazy, right? And so in a forest, every tree has a vote. So like every tree in an ensemble is given the same data, and they all make their own vote on that. And then all the votes are collected, and the one that's the majority, or not even the majority, the plurality usually, the plurality wins, and that's the output of the model. It's like voting, like in November. Make sure you register to vote, y'all, for those who can. So yeah, that's similar process. It's called voting. And so when we get to forest, what we can do is add randomness to the process, which allows us to create what we call a random forest. And so who loves democracy? So random forest, this is just an example of the overview. Like let's say we had a couple tree models here, and we wanted to figure out what type of fruit is this. We give each tree just the apple. It gives out its outputs. Two of them think it's an apple. One of them thinks it's banana. And we take them all to the vote. We check what the majority is, an apple, and it says it's an apple. So in making our random forest, to add that randomness, we do two main things. One is called bootstrapping. And bootstrapping is basically the idea of you is called sampling with replacement. An example you might have heard in a statistics class is like, if you have a bag of marbles and you take one out, you write down what it is, and then you put that marble back in the bag. That's what sampling with replacement is. And you basically, for each tree you have in your forest, you create a unique bootstrapped sample of that. And the idea is you learn some kind of truth about the data from randomly sampling it. And it helps to let each tree learn a different truth about the data. And so once we do that, now that we have a specific unique training set for each tree in our random forest, we then start to train the trees. Same process. We start splitting. The other thing that what we do in random forest is that we randomly choose what our feature we're going to be splitting on. Because like if you have a decision tree, you could have like 30 or 50 or 100 features. And you don't want to have to go through every single point, every single split, especially since trees can get massive. That's really slow and kind of teaches the model the same things every time because bootstrap sampling can only do so much. So what random forests do is for the decision trees is that you just choose a random set of samples for each decision. Like if I'm at decision, if I have like apple, I'm looking at what does the skin color look like, what does it taste like, how large is it, etc. I just choose a certain number of them. Like I only choose to look at what does the skin color look like and what does it smell like. And I just choose those two, and I have to check from those two which one makes the best decision. And so when you do that along with the bootstrapping across a whole bunch of trees, all the models will be very, very different from one another, which is important. When you're ensembling, you want your models to be different. You don't want them to all be very similar to one another. And that kind of leads to just the same models coming out with the same output. Different model, because the idea of ensembling is if one model has a deficiency, the other models will not. And so each model will cover for the other. And the result that you get is a collection of unique trees that are extremely powerful for tasks like classification. So anyone have any questions? No? Cool. So let's check out the notebook. I have our tiny URL here of 102 ml. We also have a QR code for the scan. And I will be stepping away to refresh my water. If you have any questions, Alejandro's right there, and I will answer any questions on Zoom. Just put them in the chat. I will be right back. I cannot believe the right count of this board is broken.
Just out of curiosity, how many of you were familiar with at least one of the concepts that were talked about? Ish.
In terms like what's in terms of like separating data?
I guess I was referring to like KNN, SVM, or the other one that he talked about, like specifically. But if you know about separating data, it's also good. Yeah, that's very good. Okay, yeah, interesting. Good, good.
I wasn't there for the first workshop. Is it kind of build on it, or?
Yeah. So the first one, he did something called logistic regression. I guess, are you familiar with linear regression? So that's when you have like, I wish I had a marker. It's like when you have like, do you have one?
I'm sorry, they have one.
Yeah, now I want to explain. Oh, there's one here, but it's.
It's really thin.
All right, we'll see if this works. So linear regression is when you have points like this, and then you're trying to find like what's the relationship. So the regression is like this line here. So you find this line, like by calculating the distance between these points, you find the line. So he did logistic regression last time. Yeah, because he's asking if it built on each other. So logistic regression, it works for Is it classifying two different things? It can be multiple, right?
It can be both, but it's purely for linear. It's purely for like linearly splittable data.
Okay, yeah, so like,
What can be bad? It's basically linear regression, but just wrapped to be doing logistic, and so it's not very good.
yeah, so before you showed a classification method, but the data has to be linear. For these methods, it doesn't have to be linear. So like, I guess. Yeah, like, now you can like draw a circle and separate it like that, or like do like those bricks.
Mhm.
Um.
Yeah.
For like, what is it, like multi-dimensional?
Yeah.
But yeah.
The thing about so SCMs do build on top of like logistic regression in the sense that one, they have the kernel tricks which allow for nonlinear splitting, which logistic regression doesn't have. And two, it forces the idea of, well, you can have a splitting line. It's going to give the best one possible. It's basically an advancement of logistic regression to give the best possible splitting line, dot period. Basically improving what logistic regression does by actually making it as good as a line can be, and then adds a couple more techniques to allow for nonlinear data. Cool. So has everyone been able to open the notebook and everyone has like a view of it? Awesome, good. Because last time we did not have that, and I figured out what the issue was for that. Cool. Ooh, so let me recording. Awesome. So for those of you who have it open, first things we're going to do is we're just going to create a copy if we don't want to edit the one we have here. And so now everyone should have their own individual copy. You just have to go to File, Save a Copy in Drive. Simple as. And so next, we're going on to Machine Learning 102. I'm just going to connect to our runtime. And so welcome to the Machine Learning 102 notebook. This is like before, like Machine Learning 101. This is just going to be an interactive notebook to let us like actually do the coding of it and run the code in individual cells once at a time. Like before, this is just a very large set of imports. This is something you can, if you're just writing your own models, you can copy over, or you can just look the sklearn library. It's very easy. The documentation's there, and anything you need, you can see it on each one, and just it's very easy to search up. To walk over it, this is the pandas library. This is like the spreadsheet program, like Excel, but just a Python library. NumPy lets you work with like lists and arrays, and it's very easy. Makes everything a lot easier, much faster. Because Python is actually really slow compared to like C++. So NumPy is written in C++ and then has a wrapper around it in Python. So you're really calling C++ code, which is really convenient. Then Matplotlib is a plotting library. It sort of lets you view your data, just generate nice, pretty pictures of it. Time is just time library. It lets you find the time, lets you control dates and all that. And then you have sklearn. sklearn is the machine learning library that we're going to be working with tonight. And there's a lot of things here. I'll walk through them a little bit. One is SVM. This is the support vector machine portion of the library and has just different support vector machine types in it, like linear SVC, SVC, SVM. We're going to be working with SVC, which is support vector classifier. So we're doing classification tonight. Next is train test split. If you remember from our previous workshop, this is the function we use to split our data sets into the training set and the testing data set. Next is from Ensemble is random forest classifier, which we just talked about. And then below that is from tree, which is our decision tree classifier, and a function that is called plot tree, which will let us do a visualization of our tree, which is all what we like about decision trees. They're very visualized. Then we also have k-nearest neighbors, which is just k-nearest neighbors, just their implementation. Then for metrics, we also have a couple of things here called confusion matrix, which if you remember from our previous workshop, basically just like a grid that tells you the actual label is this, and this is what the model thought it was. And it helps you show you like where the model is doing well and not. And then the Matthews correlation coefficient here, math CORCEF, is just another metric similar to accuracy, or sort of weights it to give more weight to the incorrect more weight to classes in your testing that are like not a lot there. Like if you have 8 apples and 2 bananas in your testing, the 2 bananas will be given more weight. We're not going to work with it tonight. This is just accuracy, but it's nice to have. This is counter. This is just a convenient library that is part of Python's collections package. Just counts things in a list. This is standard scaler. So this kind of scales all your data to 0 and 1. We're not going to be working with this tonight either. I was testing with this earlier, and this is a good thing to have if you want to play with it later, is that in most machine learning, we scale all our data to be between 0 and 1, so that like one dot feature that's like maybe 1 to 10,000 and another one 0 to 1, like the 1 to 10,000 doesn't dominate the model, but the ones we're working with tonight are around the same range, so we don't need it. Then we have our data sets, which is just a sort of wrapper around some data sets, like the iris data set we will be working with. Decision boundary display is just a visualization function, so we can show how the model is dividing our data. There's the same logistic and linear regressions from last time. Another train test split. I didn't check all my imports, because in Python, if you import the same thing twice, it doesn't break anything. And then there's a couple metrics here. You don't have to worry about them. And then I guess I'll go over them. Mean squared is mean squared from statistics. This is these are all statistics, and then this is just a confusion matrix calculation and a display. If you've taken statistics in high school, you know what these are. And then you have Seaborn here at the end. Seaborn is like Matplotlib. It creates nice, pretty plots. Seaborn kind of gives you more plots you can generate, and they look slightly nicer. We're not going to be working with it tonight, but it's very nice to have. You will, like, if you're working with Matplotlib and you want to make some very nice plots for doing your data analysis, use Seaborn. So, like we just talked about at the beginning of the presentation, we're going to be using the iris dataset. And the iris dataset has 150 samples, 50 of each flower type, and that contains 4 numeric features: the sepal length, the sepal width, the petal length, and the petal width. And these are all in centimeters. So since here we've already imported the data, we call just the same data sets from up here, and then we say load iris. But now we need to split this data. So who remembers what function we used to split it? You don't have to speak up. So what we're going to use is the train test split that we covered up here. This is the same one we used last time. So we're just going to write how we're going to split it. So we're going to first do our x's in our test. And so we're going to set the equal, and we're going to go train test split. And so tonight, while there's 4 features, tonight we're just going to look at the first 2, the sepal length and sepal. Yeah.
Okay, Nick, I want to just make sure everybody understand why we're doing training and testing.
No, if you feel that great.
No?
Yeah. Oh, absolutely. Oh, I guess this is something I covered in the first presentation. Do
Yeah, I
you?
wasn't here.
Okay, I'll just go into it super quick. So we basically want to train our model, right? We only have so much data. We have to split it into, again, the training and the testing. So we're going to train it on this little subset. I guess it's usually a bigger subset,
Yeah.
and then we train it or we test on a smaller subset just to make sure that it works. And then with whatever you have from your testing set, you would usually use that as some sort of intuition of how I would perform in like a real world scenario. Usually you gotta be, I guess you gotta include more data than just like the training and the testing. That's what it is. It's kind of like a check to make sure that at least in the data set that you have, you're learning what's in there.
Yeah. Think of it like this. The training set, like let's say you're taking an exam for your midterm. The training set is your practice exam. You're going to keep taking that over and over and over again till you get a 100. But then the testing set is the actual midterm. Different set of questions, same topics, but different questions. And what you want you or the model to know is that to actually have learned the knowledge and not just learned the questions. So that's what the training and testing set is for.
Yeah, yeah.
So like we did before, it's just train, test, split. So if we're going for, so the way this is structured is
I
it,
also have a question here, the iris data set.
Yeah.
Are these, like, is it a list of 2D arrays? Is that what it is? Cause it's images, right?
Mm-mm.
No?
no, just four numeric features, just four, it's just four variables.
Oh, okay, so it's not that Polaris we saw before.
No, it's that grid of points we saw before.
Oh, okay.
Yeah. So, yeah, so we'll just look at it. So for this, the way it's structured is, in train test split is structured, is that we have our X, which is our model input, and our Y, our model output. Then we have our test size, which is just a sort of percentage of what we want to be in training. With what test size is how much we want in our testing set. Like if you put 0.3, then 30% of your data goes to the testing set. And then finally you have random state. This is just a variable to control the randomness. I like to use 42 because 42 is a funny number if you know. If you know, you know. You don't need to read Guardians of the Galaxy. That's a great book series. So yes, that's what I meant. I'm talking. So for this one, since we're going to be looking at the first two features, the supple length and width, we're going to just do, we're going to do what's called ::2. Basically what this is doing is this is grabbing all of the rows in our data. And then this is just grabbing the first two features of them, like the first two columns. Then next for a Y, we do just iris.target, which is what we're targeting. For test size, tonight, normally we do it smaller, like test size is usually 20 or 30%. For demonstration purposes, it'll be 50% tonight. And then next, we just do a random state, which is like 42. So we run this. Oh, first run this. You have to run this cell first. Make sure to import everything. I forgot to do that.
I have another comment.
Yeah.
So who knows what target means here? Alright, so this iris dot target part.
Target is what we call the ground truth.
Yeah.
Basically. So that's our correct answer that we're trying to manipulate basically.
Yeah.
That's I guess, is that like machine learning lingo? Yes,
Target?
yeah, I mean, like. As it is used in this scenario, right? Like, why is
Yeah.
it not called ground truth? I don't know.
And because it's the value, it's the variable you're targeting. Like if you have your iris data and then you put it through your model and you get your output, does it equal target?
Yeah.
Yeah. So now we just run it and it should be successful. So let's take a quick look at it. We look at our X train, you can see it's a array of multiple values with two columns, which is exactly what we're expecting. And then we also have our Y train, which is just a series of zeros, ones, and twos, which are each of our classes, because like we had three types of flowers. So cool. And also plot it. So who's familiar with scatter plots? Awesome. Yes, scatter plots. So what we can do is that we can use that matplotlib library before, the one up here, matplotlib. And we can just call scatter. Nope, we don't want to call here. I'm going to just hide that. And then so we want to show, so let's actually take a look at our data. We want to look at our X train and see like how it fits to our Y train. We're going to do PLT, that's scatter. And so when you do scatter, it's going to be a 2D plot. And we kind of need to call X train over 0. So we have to grab all the rows and then the first column. Then Y, then X train will come with 1. And then. How do we shade these? And if I remember correctly, although I may not, then if we want to color it, we just do C for color. And then we're just going to set to our Y train. And then to plot it, we just do PLT dot plot. And there we go. And so here we just have a sort of plot about our data. We have the three groups that we had before. We have group 1 here, which is very obviously different. And then we have our plot, then we have our groups 2 and 3, which are very, very mixed up. It's not looking very easy to just make an easy split on. It's going to be very tricky. So after that, now that we've looked at our data, we kind of see how things are grouped. Next are just some helper functions I've written. You don't have to be concerned about these. You just have to run the cell. If you want to know what these are, this one's going to let us sort of give a plot of this same plot, but we'll also have lines showing how it splits. And then this one just lets us like run the accuracy tests of our model, see how well it's performing. So first, the first model we're going to cover is our k-nearest neighbors, like we talked about before. It's a very similar model that sort of just looks at what are the most common values. Like this star here, if we had k equals 3 neighbors, we would just have 3, we would just call it purple because purple is the closest to the 3. But then if we looked at the 6, we would have yellow because there's 4 yellows and 2 purples. So tonight we're going to be doing 2 things. First, we're going to be implementing our own KNN because KNNs are the easiest models to implement. And then we'll also be testing with sklearn's KNN. So for implementing a model like KNN, there's 3 functions we need to implement. The initialization function, our fitting function, which is what we do for which fitting is another term for training, and then our prediction function. So as we've tested before, one of the features we do need to care about is K, which is just the number of data numbers we looked at. The second one we need to look at is actually distance. And distance is important because we need some way of saying how similar a point is to another. Like when we take this point here, we're going to check it across every single point and figure out with that distance function how far apart or really how similar they are. And then we're going to do a sorting where we'll sort everything by that distance and grab the closest ones. So for our KNN, first we're going to cover the initialization. And in Python, for those who haven't done object-oriented programming, these are just input parameters, but they are not what we call attributes of this class. Like when we create a specific instance of the class, like we create a this is like a template. Like this is like a template of a car. Like there's a design of a car out there, but there's no car yet. Once we come to down here and we call it, then we've made a car. But we need to first design the car. So here for our KNN, we first need to set some attributes, which we control with what we call our parameter. So this is simply just like self.k equals k, and self.distance equals distance. And it's simple as that. We're just saying, based on these inputs, this class will specifically have these values inside them, and we call these attributes. And so for fitting a KNN, this is also very similar because in a KNN, we're just checking across all of the data. The way we train it is that we just save the data. So we're going to do self.x equals x, and then self.y equals y. Simple as that. So once we get to our prediction function, we're going to have 3 steps. We're going to have step 1, measure the distance from our testing point to all of the points. Like before, like we said before, we have our points, we have to check all of them to figure out how far they are. Then we have our step 2, which is find the k closest neighbors. So we're going to sort them And then we're gonna find out from that sorting, which are the first K that are closest. And then finally, for step 3, we're going to count the labels of the K closest. This is like what we did here. Oh, sorry, and this is like similar to what we did here, where we have our point, and we're just gonna look at what the classes of each point are. So X test is usually not just a single value, it's like a list of values. So first, we're going to create a list of what we want to output, which we'll just call like Y predictions. I misspelled predictions there. And we'll just create that as an empty list. And then next, we want to go is through every X in our X test. Like we're going to iterate through each unique point in our X test. Like if this would be one, but we could have other ones. I'm just going to indent this slightly. And we're first going to work on our step 1. And so there's 2 popular measurements in K-NANs. The 2 popular ones are Euclidean distance and Manhattan. And what Euclidean distance is basically, since I don't have a note, Euclidean distance is a sort of, if you have a point X, like X1, Y1, and then you have a second point X2, Y2. Like let's say you just had it here. We want to find how far these 2 are apart directly. And the way we do that, if you remember in like algebra, they do x squared, x2 minus x1 squared plus y2 minus y1 squared. Right? Everyone remember this from class? This measures it directly. This is known as Euclidean. To return to recording, right? Yeah, so this is Euclidean distance. Easily understood, right? The other type of distance is known as Manhattan distance. And Manhattan distance is basically like the idea of, instead of trying to find the direct closest distance, you go, what is the distance horizontal plus the distance vertical? Like if you were going down a city grid, if you had a city block, you can't cross a block directly. You can't just walk through the middle of a building. You have to go from one street to the next, to the next, to the next, to the next. And so Manhattan distance is the same idea. Basically what it is it's basically just the sum. This is, for those not familiar, this is just the summation symbol of like I equals 1. Basically, we're just going to sum the absolute value of each of our sorry, I'm losing my voice. We're gonna I'm overcomplicating this. Basically, what we're gonna do, we're gonna just sum the absolute value, the difference of the absolute values.
Can you try maybe searching to see if you can find like a visual example?
Yeah, I can. Yeah, that's hard to see, isn't it?
So, that's pretty good, yeah.
Here's a good example. Like if this is our block, the Euclidean distance is just directly, it's like if you had a triangle, it's just C, the hypotenuse of the triangle. Well, Manhattan is if you went down both legs of the triangle from one point to the other. Intuitive, right? Yeah. So these are the 2 most popular for doing distance measurements for K-NANs. So we're just going to say first we're going to be trying to measure distance. And we need, since we're going to be doing 2 of them, we're going to just say like if distance is Euclidean. And so this will be the step if we're doing Euclidean. And so like before, I will put up here. Yeah, so this is my voice. Yeah, so this is the equation P of what we're going to be looking at here. So this is what we're going to code up. Oh, sorry, make sure to put self.distance because we need to refer to the distance that we've set in our initialization. So we're going to say our distances, which is basically since we have a bunch of x here, we're going to be checking against each one of these against here. And so, as you can see here, we need three functions. We need a square root. We need some way to sum these, like we need to sum all the sums here. And then we also need some way of getting an exponent. So the way we're going to do that is, I'm just going to comment this out, is we're going to do this in sort of like reverse order. Is that first, we're going to try and get the square of all the differences. So for that, we're going to use what is np.power. And np is numpy, which is the sort of our list and array manipulation. And for this one, we're going to do self.x, which is our training data, minus x, which is our testing data. And so these are the values inside here. And then we're just going to square that. And so this is going to basically do each of these squares together. Like if we just had array of 2, like 2 values, like we have 2 values, it's going to do an x squared. We're going to do an x2 minus x1 and a y2 minus y1. And what this would generate, like if we had a list of 2 and 3, what squaring would do, it would give us an array of 4 and 9. Just the same thing. So next, what we need to do is we need to sum up all of these squares. And the way we do that is we do np.sum, just a summation. We're summing it all together. And then the next thing we do is we add a little extra parameter called axis, which we set to 1. And the reason why we do this is basically this idea of if we had a 2D array, a 2D list, we got like 1, 2, 3, 4, 5, 6, ... We don't want to sum everything together into one value. We just want to sum up all the rows. Yes, give me. And so axis 0, it basically, if we went down everything here, and what if we did axis 0, we would basically just get two values of 9 and 12. Like that would be here. That's not what we want. We don't want to sum this way. We want to sum across each row. So that's what axis 1 is for. So we basically get like 3, 7, 11, ... That's how we do it. So that's why we use axis 1. It just lets us sum the values in every single row of our array. And so that way we can still preserve all of the training. And then finally, we do just the np.square root. And this gets us the square root of our values. Simple as, it's this portion. And so what this is going to create is that if we had a, if like we had points of 1, 2, and 3, 4, 5, 6, etc. And this is our self.x. And we wanted to test against x, which would be like 7, 8. This would basically just do minus 7, 8, minus 7, 8, minus 7, 8, then squares everything. Squares everything, sums them, and then square roots them. You all get the idea. Relatively straightforward. Now, if we want to do the Manhattan distance, we can just do elif, which is like else if distance equals Manhattan. For this one, it's similar to Euclidean, except our distances are just going to be a sum of our absolute values. Like what we've written before, we just want to get the absolute values of going one way and then the other. And so for that, we're just going to do distances of first nt.absolute. nt.abs is the absolute value. And so we're just going to do n+x minus x. And so next, we just do the summation. And so that is just the same thing of before of np.sum. And then the same axis of 1. And so now we have both of our distance metrics. So next, we need to find the k closest neighbors. For that, we're going to use we're going to use two commands. First, we're going to find the nearest indices. And basically, when I say nearest indices, what we're going to do is like, let's say you have a matrix, you have an array, like 6, 7, 3. When we normally sort it, when we just like call sort, we will then get like 3, 6, 7, right? We're going to sort the values. But what if we want to know, the sorting of the indices to know which index is actually the smallest? Like, for example, this is 6 has index 1, 6 has index 0, 7 has index 1, 3 has index 2. And we want 2 to be in the front because 2 is the smallest. So what we do is call a different sort called argsort. An argsort is going to just sort the indices in a way that tells us which one is smaller based on another given array. So like here, this would be 2, 0, 1, because 3 is the smallest in this array, so 2 is going to be front, and 6 is the next smallest, which is at index 0, so 0 will be up front, and then 7 will be next, and then 1. Understandable? Yeah. Well, so for that, we're going to use NumPy again, and we just call argsort, and we call it on our distances. And so now we're going to get an array of which indices are the closest. The next we're going to do is call the self.k. And what this is doing is when we call the self.k, it's like basically this tells us how far ahead to look into our array and stop there. Like if I said I wanted to look up to 2, I would look at 2, and then I would look at 0, and that's it. So all I would get is 2, 0. And so this helps us to just cut off and say, okay, we're just looking at the top k now. And so this helps us to get the k closest indices. And so these are the k closest neighbors. These are the values with the k closest neighbors. But now we need to know the labels of the indices. We can't just knowing which indices are closest is great, but now we need to know the label. So this is where we come to nearest labels. Then we do equals, and then we just do self.y, and then nearest indices. And this is basically just calling the index of the array. Like if like here we had an array and we did like array 0, we would get 6. You all familiar with this? With Python, you can give an array of another, you can input in indices another array. If I did 0, 2, this would give me an array of 6, 3. And it's just a convenience tool, so you don't have to call each index one at a time. So now what we get out of this, we get all the labels of the k closest neighbors. And next, now that we have this, we need now to count what the closest label is. And so we can do this. We can say, let's just say this label, and this is where our counter comes in. Given our array, we're just going to count all the values in it and figure out how frequent each value is. And so we're just going to call nearest labels. And then a convenience function that counter has is that we'll call the most common, which is just going to give us the most common value in there. And we want the most common one. And then we do 0, 0 to just get the actual value itself. Like, cause this will be wrapped in a couple lists. So we do 0, 0 to just get the value. And then now that we have our label for that particular prediction, you can just append it to our label. And then finally, now that once we've done it over each value in our testing set, we just return, and we now have an array of all our predictions for all of our test values. We just return an np.array, which just converts it from a Python list to a NumPy array, because working in NumPy is so much more convenient. And we just do return for our predictions. And that is a KNN model. It's very simple. Let's just run this out. Everything worked. Now let's test out the model. So here I've set it up so that we have 3 neighbors and our distance is Euclidean. And so what we do is we first do .fit so that we will actually train the model on our training data. Yeah.
So who here is familiar with object-oriented programming? It's a 2, 3. So I guess I just wanna like elaborate on like why this is happening like this here and what Nick is doing, he's creating a KNN class, right? He wants to have a class we can call it, like some other data point with a different data set. And these initializing, fit, and predicting functions, if the data is in the same format, it should work for the other data sets as well. So that's kind of what this is for. It's kind of like a reusability
Yeah,
kind of thing,
like a
right?
template.
It's like a template, right? Like it's for organization. Doesn't have to be like this exactly, but this is quite nice. So that it works because then you can use it with, especially like when you get into like more like real world problems and you want to apply it to like another data set that you've never used before, like this is the way that you would want to do it.
Mhm. Exactly. But yeah, so as now that we've developed it, we now have we first create an instance of it. So we create a unique version, we make a unique copy of our KNN, and we want this one to have 3 neighbors to check for and use Euclidean distance. Next, we call our fit function so that we train our model. And then finally, now that we've trained it, we call our prediction, we call predict to make predictions for the model. And then we call our testing model to get the accuracy. We can just run this cell. And so once we run it, we get an output of all the ground truth test values and then our predictions. And our model had a 76% accuracy. It's pretty great. I really like that. So
What if we make it Manhattan distance?
great question. What if we do make it Manhattan? Same thing.
Hmm.
But what if we change the neighbor size? There we go. If we change it to 1, we do a whole lot worse. What if we do 20?
I guess no, because you know the way I think like at some point it finds the elbow, right? So like
Yeah.
it'll max out.
Oh,
at
there
some
you
point,
go.
Right?
Oh, well, if I change it to Euclidean, do k equals 20,
Oh, but
now it's 80.
that's it.
Yeah. So as you can see, changing your k, how many neighbors you check, and then checking your distance can have a lot of effect.
This could be a little misleading, right? Because like we know there's not 20 clusters, is there? There should be 3 clusters, right?
No, the k is for how many neighbors you check.
Oh, okay.
It's not how many clusters there are, it's how many neighbors you check. Remember? It's like up here. You're checking how many neighbors to check near your each testing point.
Oh, right.
Yeah, so cool. Now that we've coded up our own, let's try out scikit-learn. Because scikit-learn is going to let us just do a lot more and has a lot more features. So let's create a sort of list of models. First, let's just, for this one, we call, well, I'm first here to creating like an array of it. Let's call k neighbors classifier. And this is just what sklearn names theirs. And so we can set, for example, like this one, n neighbors, which is just their version of k. And let's say our original 3. And then we can do metric equals, metric is their term for Euclidean, their term for distance. We can just say like Euclidean. Then we can test some other ones. We can say, like, let's just do the one that we did know worked well. Any distance Euclidean. Let's do like a k neighbors classifier. And then like, let's do n neighbors equals 20. And then we can do our metric is like Manhattan. That's the other one we did. And then you can do k neighbors classifier. And then we can do like n neighbors equals 20 again. Metric equals Euclidean. And then if you remember during our presentation, we talked, you mentioned the idea of weighting it based on how close it is to the similar point. And we can do that with in sklearn with a thing called weights, and we can just use it as distance. And then for this one, we can also set up a couple titles for our model. Let's just create a couple titles for these names for our display. Call this like KNN k equals 3, Euclidean, and k equals 20, Euclidean. Nope. Why are you yelling? Oh, I had to leave that distance there. I meant to type metric. And K equals 20 Manhattan. And KN equals 20 Euclidean. And then we're going to say distance, so we know which one we're talking about. And I'm just writing these tiles so that when we then call our plot models, our community code, when we feed in our models and our titles. Oh wait, first thing we have to do, oh, I forgot another thing, that we need to train each of these models. So we're going to call like model.fit. So one thing, so we're going to have our models here. We're going to do an empty array. Actually, models fit. Let's do that. So then for model in models, like, so we have a bunch of instances here, but we need to train them. So let's just do model dot fit. Actually, we don't even need this. I forget. So for this one, we just have to call the fit. And we can just call like fit on X train and Y train. So now we're going to train all of these models on our data. And then we can just call models after that and see what happens. And so we've now trained each of our models. And now we have, so what you're seeing here is two things. One, up on the titles of each of these plots, based on the titles we gave, which match our models, is their accuracy. And as you can see, when we did K equals 20 and we did Euclidean, we got a 78% accuracy. That's pretty great. And then what we're also showing here is how the model sort of learns how to split the data. Like we're learning, this is a visualization of how the models learn to split things. So as you can see in the Euclidean, like it's very jagged borders. They're sort of like circles around some of the red points. And then when we had more neighbors, it got a lot smoother because as you smooth it out, it's going to just look more and more. And that sort of majority is going to start dominating. Then if you look at something like Manhattan, though, as you can see, it's a lot more straight lines because that's what Manhattan does. It just goes straight lines. And then if you look at using Euclidean with distance, it's different. So as you can see, changing the tuning of the parameters will affect not only the accuracy, but how the model learns how to split things at all. So this is what it looks like with KNNs. But what about what we talked about before, support vector machines, where we're going to try and find a nice optimal splitting line. For this one, we're going to just try something very simple. We're just going to first just show off what it looks like to call an SVM from sklearn. So for this one, we're going to just call our SVM model. And for this one, it's as simple as calling SVM, which is sklearn's SVM library, and then we call SVC, which is support vector classifier. And then for our kernel, we want to set it to linear. Like what we talked about before, we have a couple different kinds. We have three types of kernel we're going to look at: linear, polynomial, and RBF. And so when we just call SVC, we just create an object of it. And so then we're going to train it. So we're going to do SVM model. Like all the other ones, we do SVM model.fit, and xtrain, and ytrain. So we just create a simple model. And now we're going to just test it. And like all the other models, because this is how it works with sklearn models, that all you have to do is call fit, and then you just call predict. So we're just going to call xset. And then we generate a set of predictions, which we can then test with our good old test models. And we're just feeding our predictions. And this is our VSC. And so this is what our linear SVM says the output is. It says it's at 76% accuracy, which is pretty good. It beats out quite a few of our KNNs. Doesn't beat out the KNN 20 though, which is interesting. So now this was the linear one. This is where we were just trying to draw a straight line through our data. But we have some other options for our kernels. So let's try out a couple ones. So we're going to do the same thing as we did before with the KNNs. We're just going to create a sort of list of possible options. So we have like our SVM.svc, and then our kernel, it's going to be the same as before. It's just a linear one. It'll be our sort of our linear model. And then let's do another one. Let's do our SVC. And then kernel is poly, which is short for polynomial, like our ax plus b. And then let's say our degree is 2, which would be x squared plus x plus c, 1. So that's what it is. Polynomial, that's what we're going to learn. Well, like linear is just mx plus b. And so next, we can also look at one with like a larger kernel. Like let's say we want a degree of 5. The x cubed plus x fourth, x cubed, that, you get the idea. And then finally, let's look at the RBF kernel as the final other model. And so there, we also can train these ones. Make sure to add commas to your lists. That's very important. And then for model in SVMs, then we do model.fit. We just do our x train, y train. And so we are just going to call this. And so all our models have been fit. And so let's check the accuracies of each of these models, or models in SVMs. Here I'm just going to do a print statement to print out which model we're looking at. Then I am going to call on our prediction, the model.pred, predict, and x test. And then test models, print, and then just another print statement to make things shiny. And so as we can see here, we are now training with a couple different kernels. This is the same kernel we used before, the linear, it's 76, but look what happens when we do a different kernel. Just doing a simple 2-degree polynomial kernel, like x squared, we've now bumped up our accuracy 1.33%. Nice. Now doing a 5, it fell off. Not very nice. But like if we do the RBF, which is the one that like does all the circles around the point, that worked very well. That got us to 81.3%, which is very nice. And like before, we can also do our visualizations. So I'm just going to make a couple of titles for these ones. I'm going to call this one linear, call this one poly 2, poly 5, and RBF. So like before, I'm just going to call our plot models, and I will feed in what I call it, our SVMs, then our titles. We're going to let things plot. And this is the plot of our SVMs. And so as you can see, it's very interesting how the sort of curves form. Like if you can see with the linear model, it's actually just trying to split things down with straight lines. It's like logistic regression. It just wants to create dead straight lines to just split everything. But our data is not linear, is it? It's not, our data is all mixed up. So by doing like poly 2, we're adding some curves to our lines to how we split. Not just an exact split, we have like some curve here. And then when we get to poly 5, as you can see, it curves a whole lot more. Now we're like really looping it around. And then finally, if we look at something like RBF, now things curve a lot more and we can sort of shift our points around. So how you choose our kernel, again, changes how our decision lines are made. And so, as you can also see with RBF, RBF is usually the most popular because it's the one that does the best results. So we've now looked at 2 types of models, KNNs and SVMs, very popular. But now we're going to get to the fun one, the ones that are always very nice to look at, decision trees. So decision trees, like before, you just go down and make decisions. And they're split based on the purity, which is basically how much, if you split one way or the other, you get 2 leaves from that node that are more easily able to say whether a point that arrives there is in one class or another. Like if you arrived here, you can very clearly say yes, if someone orders free coffee, to accept it or not. But if you're up here, you don't know whether just from salary. Let me rephrase. Again, here's a better one. Like if you're at commuting more than 1 hour, it's not immediately obvious which one is the best decision to make if you just like looked at everything. So you have to figure out which one's the best split. All right, I'm moving away. So for decision trees, like as any other models with sklearn, it's as simple as calling decision tree classifier. And so we just create an instance of that. And so like that, we just call xtrain and ytrain. So we're not going to train it. Easy as that. So we create our preds. We do our tree.predict of our xtest. And then we call our test model of our predictions. And so looking at it, that is the worst model we've had so far. That's not even at 75%. That is the single worst model we've had. Why might that be? Decision trees are supposed to be great. They're supposed to be amazing tools. Well, let's visualize the tree. I have a little bit of code here that you can just run to look at sort of how the tree looks like inside. And as we will see in a minute, this is why. It's massive. That's a massive tree. This is a great highlight of the problem with decision trees when you don't control them. They will just split and split and split and split and split and split and split until it just looks exactly until every point is one class alone. And so it's overfit. It is so overfit on the training data that it's not very useful. So we need to add some controls on this. We can't just let it go on and split and split and split until infinity, because that's how you get messes like this. And can anyone really interpret this? Is this easy to interpret? No. So two very helpful controls for controlling a tree is what we call the maximum depth and the minimum samples. And so maximum depth is exactly what it looks like. The tree can only go so far down. Like if we had a depth of 2, after this line right here that I'm drawing, that I'm kind of pointing out with my mouse, you can't have any more leaves. It would just stop right here. Then it's done. And then the other one is minimum samples. Like let's say, for example, here, I can't zoom in thing. Like here, 26% of all the data in our training set is at this node. And let's say you can't, and let's say you tried to split, meaning you have to have at least 25% of the data at any node to be allowed to split. You could split here, you could split here, but once we get to here, we would say you're done. You can no longer split at this node because you have less than 25% of the data. And this is helpful for for helping to prevent issues like this, where we're just trying to split and split and split so that each individual value gets to go to their own unique leaf, because that's just a massive sign of overfitting. Like there's only one value here, there's only one value here, one value here. It's not helpful, it's not useful. So for creating a control tree, we're going to create another model. I'll call this limited tree. And then it's going to be the same decision tree classifier. And then we're going to have a min samples split. This is just the minimum samples for our split. And let's say we want a minimum of 5 samples. We want at least 5 samples of the data to be available for a split and no more. And then let's say our max depth is 5. We don't want to go more than 5 layers deep. So we can call the same thing before. It's just train and train. And so as you can see, we've had our controls. Then we can do the limited tree, predict. We can do xtest. And then we can do test models on our right. And our accuracy is up. We went up 7%. That's great. So why did we do so great? It's great. We added some controls, but what does it look like? What did our model look like now? And so with it, we now have a much easier to read tree. Like we can now just see very clearly, like it starts here and it's looking at the sepal length. And then if the sepal length is less than 5.5 centimeters, It's gonna go down here, and so this helps you divide difference between setosa and virginica. Can't speak. So, but as you can see here, the tree is much more controlled. It was much more controlled. The splits are, like here, the splits, like this particular split, as you saw before, isn't getting out of control. And then like the splitting here, it just helps to, now that we've limited how much the tree can like grow, we now are able to help fight the model's overfitting. And so that's how we're able to get our 7%. But as you can still see here, there's still some overfitting. Like you're seeing like a one value here or one value here or one value here. We would, yeah,
Just gonna, so who knows what overfitting means? Okay, so overfitting means when, can you pull up like an image, because it's also,
yeah, I guess so. Basically, overfitting is like overfitting. You remember that idea before I gave about taking a practice test as your training set and then the actual midterm as your testing? Overfitting is basically you memorize the questions and you only memorize the questions on the practice test alone. Like you know those practice questions and you could get all those practice questions right, but you only know those practice questions. Like you memorize the answers, but you have no clue how the math works. So when you actually go to take your midterm, you don't know how anything. All the questions are new and then you fail because you only memorize the questions.
yeah, so, could you go to that loss curve one on the bottom right?
This one?
This one. So the overfitting part basically means that you're gonna keep learning your training set. But when you go to validate it or test it in the validation, there's gonna be like a breaking point. And this is the overfitting point, that you keep learning your training. So you're getting that 100 in the practice test, but your testing, it's not reflective. So you wanna prevent this.
Yeah.
You would usually, I'm assuming at a later workshop, we're gonna learn about this early stopping.
Yeah.
Where you basically stop training because there's no point in learning anymore because you're gonna,
Yeah.
like your error is gonna keep going up.
Yeah. Thanks. Thank you, Alejandro.
Yeah.
So cool. We can also look at how the tree is doing the boundaries like we looked at before. So let's create just a couple titles for these. Call this decision tree. Then we'll call like controlled decision tree. And we'll just do the same models as before. We'll do like a tree, another limited tree, and our titles. And we can look at how they look. And as you can see here, there's sort of a visualization of how the trees are learning to sort of split the data. And as you can see here, the uncontrolled decision tree has a very jagged border. Like it's going all over the place and it doesn't really look like it's learning the data. Like, why is there a red dot here? There's no red dots here. There's just one in the training set. And it's like all over the place in this sort of grab bag middle area that doesn't really match well to our testing data. But when we control our tree, as you can see here, our line is much smoother. And so this much simpler boundaries between points is letting us have a more accurate model and avoiding the overfitting that you're seeing here. So, but there's still problems, like maybe we could do better. So this is where we get to random forests, which are our ensembling technique, where we basically just now have a bunch of different type of trees. And each of these trees is unique from one another. And so all these trees will kind of act different, and then they can vote together. And their voting will then come out with an output of what it thinks it is. And so we're calling a random forest. Yeah.
Is that set like this? Or is it-
No.
It's like that actual.
Yeah, like
Yeah.
ChatGPT should overfit, like it's just a matter of, if there's like a trade-off between how much computation you spend,
Mhm.
like running and training, and the amount of data that you're doing.
So it's
much harder to overfit on a larger set, but it's really. Like, I don't really know if that's true, like, it's harder as in you need more computation, but if you have the computation to just keep learning it and learning it, at some point, like, the same thing is gonna happen.
The answer is yes, overfitting is a problem, is a potential risk for all models. It's just the more data you have, the less risk there is, but it's never zero.
Yeah. Cause also at some point,
It also depends on the quality of data you collected.
yeah, like all these things are very important, and then I guess there's no like, kinda. Just like answer, like, you're not like, just stop training at this point, it's very kind of trial and error. So at this point, like we saw with the image, like it's very easy to see like a point that you're gonna overfit, but in real, like. In the real world, it's just gonna happen through an experiment, like you're gonna run the experiment, you're gonna see at some point my loss curve starts going up. And then you'll know, but yeah, no, I don't think there's any way to prevent it, right?
Just, there's no way to prevent it entirely. There's just ways to try and minimize the risk, like
Yeah.
early stopping, more data, minimizing the computational size of your model, making sure your model is small enough to not overfit on your data.
So, right now, we haven't gotten to actually, maybe I shouldn't go to this. Like, if your model is very big, it's more likely to overfit because it has kind of like more tweaks that you can make to it, right? Like,
We'll get to that.
yeah,
Yeah,
like
we'll get
a bigger tree would be more likely to overfit.
Yeah, like the tree we saw here, like this tree, like we saw here, this tree's overfit. It's massive. It's massive and it's so detailed on the training data that it's not very good on the testing data. It's learned too much about the training data. It memorized all of the practice exam questions without learning the material. Not good. Don't look at answer sheets. I mean, look at answer sheets if they're on the midterm, but looking at a practice exam answer sheet is not going to help you. But you didn't hear that from me. I do not condone cheating. AI UCF does not condone cheating on exams. We do condone using AI though. Kidding. Don't use AI in exams. You'll get in trouble.
I went through a lot of.
I have not encountered a class that does AI. Anyway, so random forest classifier. To call it, it's like everything else. You just call it. So we're going to call it random forest classifier. And since as I described in our presentation, there's like a randomness to it because like the sort of data each tree is given is different, it's random. We're going to just set it to a set random state, which is 0. That way we don't have it changing every time we train it. And so we're not going to do as before, forest.fit, xtrain, ytrain. And then we're just going to train our model. And so we're going to do our predictions. Forest.predict. X-test, and then test models. Right. And like before, we got a 78% accuracy. Great, that's even better than what we did before with our controlled tree. We've now improved it by another %. Great. That's one of the powers of random forest is that it will learn to do better than just a single decision tree alone through its ensembling. But we found controls that make our decision trees pretty good. Maybe they would be helpful in our forests, because forests are just trees. So we'll make another model, one that includes our same controls as before. The forest controlled, random forest classifier, same random state. Let's also control how many trees we're making, because if I remember correctly, the default of sklearn is like 200. No, it's 50. It only makes 50 trees. Let's say we want more trees though. So we're going to create 100 unique decision trees for our data. And so let's add the same controls for each trees we had before of a max depth of 5 and a min sample split of 5. And then we can just do the same thing before of forest control.fit, xtrain, ytrain. Cool. Then we can do our preds of forest control, fit, x-test. And then we can do our test models. Preds. Why are you yelling at me? Oh, predict, not fit. I did a typo. And now that we trained it, we have now beaten our own model once again. We have now increased our accuracy further up to 81%. Yeah, let's go. So, woo. So from just a uncontrolled decision tree, we figured out that controlling it helps to improve accuracy. Making it an ensemble with other trees makes it improve its accuracy. And then doing together improves its accuracy even more. And so we can also take a peek at the sort of boundaries it is performing. And we can use decision tree. So I'm just going to do a couple titles on this. It's our control decision tree, a random forest, and then our controller. And so we can also just put our models in a list. We got our tree. We got our tree limited. How did I name it? I don't remember how I named it. Shame upon me. I don't remember my own model names. It's limited tree. Limited tree. Forest. And forest controlled. And then, like before, we can just call plot models. More models and our titles. And this is what our models look like. As you can see before, same trees. But now that we look at a random forest, they're interesting because they look like just our normal decision trees, but with more like definition around them. As you can see here, while this decision tree tried to cover the red points that are in this space, but failed because it was trying to bridge, our random forest was able to just sort of dip in and dip out and avoiding the white points. It did even better. And then once we controlled our random forest, it then dealt with the sort of like red gap that was appearing in all of these points. And so this is the best model we've had. And it has a very good curve around most of the data. I'm sure if we messed with the points even more, we could get an even better model. And so that's it for tonight. Thank you all for coming. I appreciate y'all sticking through me and through my 2 hours now of endlessly talking. I'm sure I have covered a lot of information for you, and you would love to check over some of this, read through our descriptions that we've added for these that kind of explain things a bit more than just me talking. So for everyone here and online, the code and the slides and the recording will be published onto the Discord server in the announcement. And if you all could please fill out this questionnaire and let us know how we did tonight, that would be greatly appreciated. We're always looking to improve. Like after our first workshop, a lot of feedback was that we need to spend time more coding, which I hope we did well tonight on. We at least spent more time coding. And then make sure you come back in 2 weeks on October 30th, where we're finally going to get into Machine Learning 103, neural networks, the thing that everyone actually cares about.
Yes.
We're going to be covering neural networks, which is 99.99% of everything that's used nowadays. Yes, these other models are used, but it's like that 1.1% where neural networks aren't helpful. We're going to cover the topic of how models learn and backpropagation. We're going to get into the sorts of different neural network architectures that exist out there nowadays. And we're going to actually, instead of just working with like sort of these random sorts of data sets out there, we're going to be working with pictures. You're finally going to see cool pictures and get to see all the nice stuff. So thank y'all for coming. I'm finally letting you go. Peace. Have a good night. Have a good one.
Any questions?
Oh yeah, do y'all have any questions?
Concerns
Sorry.
or comments
Sorry.
or would want chats?
Yeah, I'll be sticking around while I wrap up. So
I'll
if
be
you have any
here.
questions.
Yeah, these things are good to know, like,
No,
I know that everybody wants to just like kind of get started, right? Like just do something, but it's really important to position yourself in kind of like the state of the field, right? Like,
Yeah.
why are we doing, neural networks now? And it's because these things only have so much power.
Yeah.
They're good to like learn here and then, and they're good for these toy data sets, but like next lecture, we're gonna learn that once we get to like the really big data sets, getting into like I don't know, even like gigabytes or even like definitely terabytes of data, you would need like neural networks basically. Not necessarily, but they're really good with a lot of data.
Here's how I like to put it. All these data sets are good, but they're like great if your data can be just put in an Excel spreadsheet. But if you're outside of Excel spreadsheets, like if you're working with language, or you're working with pictures, or you're working with like audio signals or like time series, like stock exchange. Actually, in a stock exchange, you can do these on. That's what I did them.
Yeah.
But like if you're working with pictures, you're working with audio, you're working with video, if you're working with any data most people actually care about, these aren't great. These don't suffice. So, but these are still wildly useful because one, not all data is like that, and two, you don't want to just jump into neural networks. You don't want to just have only one tool in your toolbox. You don't want to just have a hammer, you need a screwdriver, you need a saw, you need pliers.
Yeah.
You need to just have, we're covering these things first because you need to have your toolbox prepared to know what AI model do we really need for my data.
Yeah. And
Yeah.
the concepts, oh, sorry, go ahead. The concept related to like fitting and creating a model, the class, like normalizing, training, validation, all these things do remain through the different architectures. So also in neural networks, you also do that.
Yeah.
So this is giving you all those basics down, basically.
Mhm.
Like all the boilerplate stuff that is gonna be repeated throughout, you're gonna see it here and you're also gonna see it after.
Exactly. Yeah.
So when did these methods for separating data and neural networks, they come out like similar times, neural networks come out a lot later?
Oh, can I do this one?
You can do this one. You can cover perceptrons.
Okay, so the original neural network, like as like the working one that we know today came out like in 88 or 89, I think.
I mean, it kind of came more out like in 2010.
No, but okay, so like the original one was in the 90s, like 89. This was like at that time they made it, they showed that it worked.
Mhm.
But it was like the data that it was learning was really, really simple. Like it was like, I don't know, like relationships, like in a family tree or something, like a very small graph. It wasn't until, okay, before I get there, so during like the 90s, the early 2000s, they were very about like these sort of methods that.
You mind if I put it straight out, just fun?
Yeah.
They came out at the same time, but there's history on how they developed. Like these came out, I'll let you continue, but basically these came out at the same time. Neural networks, the theory of them was technically earlier. They were like 80s-ish, while a lot of these really got concretely made in the 90s. But like all the sort of actual work and development came out all in the 90s. It's just these were able to be implemented on the hardware at the time. Neural networks needed like 15 years. Anyways, you continue.
So these are less computationally expensive. So 2000s, they were very popular because they're interpretable, they're cheap to run, and they worked. It wasn't until 2010, 2011 that somebody made this paper called AlexNet, but that was basically when they started classifying images with neural networks.
Yeah.
I guess these pictures don't really say much, no.
It's
But
hard to describe.
yeah, it's hard to describe it, but let me see. Like,
Basically, the important thing to know is that back in the olden days, when GPUs were readily available and NVIDIA wasn't a $3 trillion company it is now, you could not train AI on GPU. That code literally did not exist yet. No one knew how to do that yet.
Yeah.
So everything was trained on CPU. And CPUs are freaking slow.
Yeah.
They are really slow. So training a neural network like this all looks like diagram view, but we'll explain this at the next workshop, what this means. But like training this would take forever. It was really slow, really hard to do. Memory was hell. You just couldn't do it. So we developed these other techniques that work.
So something really interesting about this one, last point, is that the guy, like the guy that did this, the PhD student, he like manually coded the GPU code himself, like on the GPU, because it didn't
Yes.
exist.
Yeah.
Like he was one of the first ones to be like, okay, like we have this piece of computation, but I don't know how to use it, like I gotta use it. They developed the network, and then they developed the code, and it was like a huge contribution. It was like, this was what you would call groundbreaking, yeah.
Which is hilarious. It's such a simple part.
It's very simple because this exact type of network even like this architecture,
Mhm.
it was like made like in the nineties also.
Yeah,
But
if
it
I
just-
remember correctly, the CNNs were made a long time ago.
Yeah, they're from like the nineties too, but they just weren't able to be used all the way to like 20 years later. Purely because of a computational issue, like we just didn't have the compute to run it.
So, does that answer your question?
Yeah, why are CPUs so much slower than graphics?
That might be like.
I can cover it. So the reason why CPUs are slower than GPUs is, the better way to frame it is GPUs are so much faster than CPUs at matrix multiplication. Because GPUs were originally designed to do graphics processing, which involves a lot of like matrices and all that, because you have to do compute shaders and all that. What the AlexNet authors did is that they utilized the fact that GPUs are so good at doing matrix multiplication, which is what all neural networks are, is that by doing that, they were able to just load training a neural network and doing all the matrix multiplication on the GPU and just zoom. It's not that CPUs are slow. Actually, CPUs are used in reinforcement learning, which is like robot training, because you can't train that on a GPU really. But when you're just training something like this, which is just multiply a matrix A by matrix B, you can just put that on a GPU. But that's why. It's not that CPUs are slow, it's just
Yeah,
GPUs
so
are fast at neural networks.
There's things that you need a CPU for that a GPU will not help you with.
So like, these type of networks just happen to be good at, or sorry, the GPUs happen to be good at when Nick said the matrix multiplication, which is what's happening under the hood here. But like a CPU is kind of where you